So how do machines actually get smarter? And spoiler alert, it's not magic. It's actually a lot like how you and I learn, by making mistakes and then, trying really hard not to make them again. Today, we're going to dive into one of the most powerful ways they do this, a technique called boosting. But before we get into the nitty-gritty, let me ask you something. Is one single brilliant expert always the best person for a job? Or could you get a better result from a whole team of specialists, even if none of them are a genius on their own? Hang on to that thought, because that's exactly the idea we're going to unpack today. All right, here's our game plan. We'll kick things off with the big idea of AI teamwork. Then we'll look at the two main strategies they use. We'll break down how boosting actually learns from its mistakes, meet the current champion of the field, XGBoost, and finally, see why this technique is just dominating in the real world. All right, first up, this concept of ensemble learning, or what I love to call AI teamwork. It's all about this one simple truth. A team of models working together almost always crushes a single lone wolf model. So here's the deal. Any single AI model, no matter how good, can have its own blind spots, right? It might be a little bit biased or just kind of shaky on certain things. And the solution? It's actually pretty elegant. Instead of trying to create one perfect, all-knowing model, we just combine a bunch of simpler, weak models to create one incredibly powerful, strong model. Okay, so what in the world is a weak learner? And no, it's not an insult to the AI. It's just a simple model that's basically a tiny bit better than pure random guessing, like a coin flip. Think of something called the decision stump. It's like a decision tree that only gets to ask one single question. On its own, it's not winning any genius awards. But, and this is the key, when you team up a whole bunch of them in a really smart way, well, that's where the magic really starts to happen. Okay, so if we're building these AI teams, how do we actually do it? Turns out there are two main schools of thought here: bagging and boosting. And this is where things get really cool, because the strategies are polar opposites. Think of bagging as a democracy. You chop up the data, give a piece to each model, let them all train at the same time, in parallel, and then they all just vote on the final answer. Simple. Boosting, though, is more like a collaborative assembly line. The first model takes a crack at it, makes some mistakes. The second model comes along, looks specifically at those mistakes, and its whole job is to correct them. Then the third model corrects the mistakes left over. You see the pattern. Let's break that down a bit more. So with bagging, everything happens in parallel. Its big goal is to reduce variance, which just means it makes the model more stable and less prone to wild swings. And like we said, every model gets an equal vote. Boosting, on the other hand, has to be sequential. Its primary mission is to reduce bias, to get closer and closer to the right answer. And in this system, it's not a democracy. The models that do a better job get a bigger say in the final decision. It's a meritocracy. Okay, so let's get under the hood a little bit. How does this whole learning from errors thing actually work? We're going to look at two really clever ways it does this. First up is a classic called AdaBoost, which is short for adaptive boosting. Imagine you start with all your data, and every single piece of information is treated as equally important. After the first model tries, AdaBoost zeroes in on the ones it got wrong and makes them heavier, so to speak. It increases their weight. It's basically telling the next model in line, hey, forget the easy stuff for a second. Focus all your energy on these hard problems that we messed up last time. Then we have gradient boosting, which attacks the problem from a totally different angle. It trains a model, then it calculates the errors, the gap between its prediction and the real answer. These leftovers are called residuals. And here's the genius part. The next model's job isn't to predict the original thing at all. Its entire purpose is to predict the errors from the first model. So each new model is literally built to clean up the mess left by the one before it. It's so clever. And this is the key takeaway for both of these methods. Each new model is totally dependent on the one that came before it. And that right there is why boosting has to be a sequential, step-by-step process. You simply can't build model number 2 until model number 1 has had a chance to try and fail. All right, all of this leads us to the current king of the hill, the champion of boosting algorithms, an algorithm that takes these core ideas and just cranks them up to 11. Meet XGBoost. Yeah, people literally call XGBoost gradient boosting on steroids. And honestly, that's the perfect description. It's built on that same smart idea of correcting errors in a sequence, but it's been supercharged with all sorts of optimizations to make it incredibly efficient. So what makes it so special? Well, check out its superpowers. For starters, it's just wicked fast and performs like a beast. It has regularization baked right in, which is a fancy way of saying it stops itself from getting too cocky and just memorizing the data instead of learning from it.
It even handles missing data automatically, which is a huge headache solved. And get this, even though boosting is sequential, XGBoost is so clever it finds ways to parallelize some of the smaller steps inside the process. It's no wonder this thing is the weapon of choice for winning pretty much any machine learning competition out there.
Okay, so it wins competitions. Big deal, right? Well, let's talk about why this matters in the real world. This isn't just an academic toy. It's changing how things get done. This has to be one of my all-time favorite examples. Remember those digital cameras from the early 2000s? The ones that would magically draw a little yellow box around your face in real time? Yeah, you've seen boosting at work. That was powered by AdaBoost. It was the perfect job for it. Combine a ton of super simple checks, like, is this area darker than that area, to build one really strong face detector.
And today, that impact is just everywhere. Just look at fields where mistakes are costly. In finance, these algorithms are workhorses for deciding who gets a loan or for spotting fraudulent transactions. In medicine, they're helping doctors make more accurate diagnoses. In every one of these cases, that incredible accuracy you get from relentlessly focusing on mistakes is not just nice to have, it's absolutely critical.
So, if there's one thing to take away from all this, it's this. Boosting teaches us that errors aren't failures, they're opportunities. And by focusing on them, by obsessing over them, we can build these incredibly accurate, rock-solid models that can solve some really complex, really important real-world problems. And that brings us to a final, kind of spooky thought. We've now built machines that are experts at learning from their mistakes. So here's the question I'll leave you with. What's the one mistake that we should all hope they never learn how to make?